Hello, and welcome to Astronomy 100. In this video, we're going to continue our discussion of Newton's laws. And remember that our ultimate goal is to understand a concept called orbital mechanics, what it means for a body to orbit around another body. Now, if you recall from the previous couple of videos, the concept of orbital mechanics is not a simple one. There's not just one simple explanation, but it's actually the culmination of a body of concepts that all together describe this action that we call orbiting around another body. And of course, what we started with was describing what are called Newton's laws of motion. And in this video, we're going to continue, but to get to Newton's second law of motion, we need to continue with some definitions. So let's go ahead and get started. Now, Newton's second law has to do with the concept that is related to speed, and ultimately what we're looking for is the word acceleration. But before we can get to the word acceleration, we have to start with the concept of speed. Now, speed is one of those terms where many people will have a feel for what it means. If I were to tell you somebody is speeding, then of course, obviously you get the idea, but to put it into words is a little bit troubling for people. So here is the actual definition of speed. Speed is the rate at which something is moving. Now, here in the United States, when we measure speed, we typically think of things like miles per hour. This is what your speedometer on your car is going to show you as you're going down the freeway. Now, if you think about it, the word mile is a unit of distance, and the word hour is a unit of time. Now, you notice it says miles per hour, and so the unit of distance is on the top and the unit of time is on the bottom. So if I were to come up with a formula for speed, it would be this one over here on the left. So the speed of any object is the distance that it travels divided by the time that it takes to do so. So an example that I have here is your speedometer showing a particular speed. And this one here is showing a speed of about, let's say, 62 miles per hour. Now, if you think about it, 62 miles per hour, what that is saying is that you will go a distance of 62 miles in 1 hour. So if you travel at 62 miles per hour and you don't deviate, never faster, never slower, then after 1 hour of travel, the time that you do this, you will travel a distance of 62 miles, the distance. So speed is the distance that you travel divided by the time it takes you to do so. Now, the problem, though, is many people mistake the concept of speed with the idea of velocity. And it is common that you'll hear people interchange these two words as if they mean the same thing. You'll hear somebody say that the car was traveling at a high rate of velocity, and maybe they're just trying to sound more sophisticated. But in reality, in the world of physics, there is a big difference between the concept of speed and velocity. So let's go ahead and define velocity. Velocity is the speed that you are traveling, but it's also combined with a direction that you are traveling at. So just the speed, 62 miles per hour, well, that's a speed. But if you were to say 62 miles per hour and indicate a particular direction, let's say northbound, then you are actually quoting a velocity. So this picture here of these cars going down this freeway, we could say that this car is moving at 62 miles per hour, but you'll notice it's traveling in a particular direction, and that direction, let's say, is northbound, and so you've actually quoted a velocity. So the idea sounds very similar. It almost sounds like it's trivial, like, well, what would be the point of indicating direction and then, of course, changing the nature of it? It sounds almost as if we're just splitting hairs. But let me give you a couple of verbal examples of this. Let's say that these two cars on the highway were to crash into each other. Let's say it's a head-on collision where one car is going in one direction and the other car is going in the opposite direction. Now, the speed of their travel contributes to, of course, the outcome of the accident. If they're traveling very fast, then of course the accident is severe, and if they're not traveling very fast, then the accident's just a fender bender. But isn't it really that the direction was really the reason why there was an accident in the first place? If they're traveling in opposite directions towards each other, then there's a collision. Notice in this picture, if they're traveling both at 62 miles per hour, but in the same direction, then there's no collision. So in physics, sometimes the direction of travel is of importance, and sometimes it's even more important than the speed of the travel. Many years ago, I had a physics class in high school, and I had a physics professor who used to like to say some kind of dramatic things to get the point across. And one of the things that he said was that when somebody gets shot by a gun, it isn't really the fact that the bullet was traveling very fast that injured or killed that person. It was the fact that the bullet was traveling towards them. So if somebody points a gun at you and shoots the bullet, it's the fact that the gun's pointed at you as the reason why you have been killed. So obviously the speed of the bullet's important, but the direction is also as important, if not more. So in physics, we need the ability to separate out these concepts, or in this case, to include one more piece of information. So velocity is speed plus direction. Now, I'm going to spend a moment to talk a little bit about math, because it's at this point in the semester that we're going to see more and more the formulas that go with astronomy and physics. And as I always tell my students in an Astronomy 100 course, we're not really all that interested in going really deep into the math. Usually in a general education class, we're not looking to make math a big part of the class. But what is important, though, is that you can understand why a formula is a piece of information related to a concept. So let me show you what I mean. Now, what I'm going to do is show you just the little tiniest amount of math that is necessary to really make these formulas become more understandable when it comes to the concepts. And in this case, let's talk about the idea of a ratio. We're going to use as an example our formula for speed, distance divided by time. And whenever you see something divided by something else, that is a ratio, something per something or something over something. Now, when it comes to ratios, there's information about the ratio that can help you understand the concept, and I'll show you that in just a minute. But let's first bring in some mathematical language to help you understand. Now, the left side of the equal sign and the right side of the equal sign are equal to each other. That's what the equal sign means. Now, this ratio on the right side, something divided by something else, will affect the left side. So if I change the top, remember the top is called the numerator. If I change the numerator, it will of course change s. And if I change the bottom, which is called the denominator, that will also change s. But what they teach you in a math class, and what is of critical importance this semester in this class, is to understand how the ratios work. The top on the right side versus the left side, you need to make sure you understand that in math, if there's nothing indicated underneath the s, there's assumed to be a 1. So it's actually s over 1. So the top on the right side is actually the same as the s, because the s is the top on the left side. So these two variables, or these two symbols, are directly related. Now what that means is, if d becomes larger, then s will do the same thing. S will become larger as well. If d becomes smaller, then s will become smaller as well. They're direct. Whatever the top on the right side does will force the left side to do the exact same thing. Now, the t is inversely proportional to the s. So in other words, what will happen is, if I change the value of t, it does the opposite for the s. So if t becomes larger, s becomes smaller, and if t becomes smaller, s becomes larger. They do the opposite thing. Let me give you a few examples here. So let's say you're traveling at 80 miles per hour. 80 miles per hour is you travel a distance of 80 miles in 1 hour. Now, what if we change either the top or the bottom? Let's say we go 80 miles in 2 hours. Now, you'll notice that the d hasn't changed. It's still 80 miles, but you'll notice we've made the bottom bigger. So if we make the bottom bigger, remember, the s will do the opposite. If the bottom is bigger, then the s becomes smaller. So 80 miles in 2 hours is going to be a lower speed, a smaller s. Of course, just doing the math, the 80 divided by 2 becomes 40, and so what you end up getting is 40 miles per hour, which is a slower speed. So notice the bottom became bigger, but the speed became smaller. Now, we can obviously do other things like 55 miles per 1 hour. Notice if I make the top smaller than it previously was, but I don't change the bottom, making the top smaller makes the speed lower. So 55 miles per hour is less than obviously 80 miles per hour. So if you just simply understand ratios, it'll help quite a bit. And we're going to do a few examples of this here in just a minute. Now, this leads us ultimately to the concept that we're looking for, and that's the word acceleration. Now, rather than a sentence, I'm going to show you a formula. The acceleration of any object is equal to the change in that object's velocity divided by a period of time. So in other words, acceleration requires something to change its velocity. Now, this is where you have to remember velocity is both speed and direction. So changing velocity could be changing speed, or changing velocity could be changing the direction. And we'll come back to that in a little bit. So acceleration is when you change your velocity over a period of time. Let me give you an example of how this is different than just speed. I will admit, my very first car was a 1976 Chevy Vega. Now, this is not a photograph of my car. I don't have any, thankfully. The car was a bit of a clunker, but it got me around town. Now, the problem with my first car, my Chevy Vega, was that it did not have a terrific acceleration. It was old and it had been beat up a little bit, driven by other people. And even though it ran, it didn't have a great acceleration. For instance, my car would go 0 to 60 like every other car would, but it would take about 2 minutes to do it. That's no exaggeration. So if I stomped on the gas pedal and kept my foot all the way to the floor, after 2 minutes of going faster and faster, I would be going 60 miles per hour. So notice 0 to 60 is a change in velocity, 0 to 60, and then over a period of time, meaning it took me 2 minutes to do it, or 120 seconds. Now let me show you a different car that also can go 0 to 60, just like my old Chevy Vega could. This is a Tesla Roadster. Now this is an all-electric vehicle, and this car will go 0 to 60 just like my car did. The end result is still 60 miles per hour, but it only takes about 4 seconds to do that. Now here's what I want you to notice. The bottom is really what makes one car have a different acceleration than the other. Both cars go 0 to 60. But notice the Tesla does it in 4 seconds, whereas the Vega does it in 120 seconds. So the fact that the bottom is small for the Tesla makes the acceleration large. So even though both cars end up going 60 miles per hour, the one that does it in the least amount of time has the greatest acceleration. Notice how the ratios tell us more about the concept. It's not the fact that they both go 0 to 60 that makes the Tesla have a greater acceleration. It's the fact that it does it in a shorter amount of time makes the acceleration greater. Now, before we get to Newton's second law, we're not going to get to it in this video, let me show you one last concept to think about. The question I want you to ponder is it possible to accelerate without changing your speed? If you recall, we often think of acceleration as 0 to 60, just like a car does, or something like 60 to 100. Going from 60 to 100 is accelerating. But let me show you an example of how you can accelerate without ever changing your speed. Let's start with a real-world example. This is near the college, near Palomar College. If you're coming down south on the I-15 and you want to go west on the 78, there's an interchange, and it's a very long curving ramp that takes you from one freeway to the other freeway. Now let's say you're traveling down the freeway at 60 miles per hour and you don't change your speed. You keep going 60 miles per hour as you gradually take this turn and you change direction. Notice your speed stayed 60 miles per hour, but what happened is you changed your direction. By changing your direction, you are changing your velocity, and you're doing it over a period of time. you're accelerating. So sometimes keeping the same speed but changing your direction is actually the same thing as accelerating. So it's very, very important to understand that it's not always changing speed that ends up meaning an acceleration has happened. Sometimes you can keep the same speed, but by simply changing direction at that speed, you are also accelerating. What we'll see eventually is that Newton says that there are forces involved anytime you experience an acceleration. But we're running out of time, so we'll keep that for the beginning of the next time. I hope you'll join me.